All right. Still no questions from the homework. 4.2 Rolle's theorem, mean value theorem, done. Not gonna need them for much, but I got them. All right, let's talk about 4.3. I told you chapter 4 is applications of derivatives and mostly graphing applications of derivatives. So we're hitting those right now. We're talking about how to find those high points and low points. And in college algebra, when I teach polynomial functions, they know how to find the y-intercept, they know how to find the x-intercept, they know how to find the end behavior of the graph. So they can do a pretty good graph of a polynomial function. But when it comes to how high does this graph go, they have no way of knowing that. In algebra, you can't find what the highest point of a polynomial, except for quadratic. You can't necessarily find the highest point or the lowest point on a graph. You just know it goes down some, and then at some point it has to turn around and come back up. So what I'm saying is, y'all are fixing to be a tad smarter than college algebra students. But you knew that already. I have cut and pasted, because I'm OCD, all the important stuff from 4.3 on one page, and that's it. The first box is theorem on increasing, or definition of, not theorem on, but definition of increasing and decreasing functions, just the very precisely worded what it means to be increasing on an interval, what it means to be decreasing on an interval. A function is increasing on an interval if for any two numbers, x1 and x2, in the interval, x1 is less than x2 implies that f of x1 is less than f of x2. That's the official definition. If you look at a graph left to right, that would be x1 to x2. If y1 is lower than y2, then the function is increasing. Just it goes uphill from left to right. And the same thing for decreasing. A function is decreasing on an interval if for any two numbers, x1 to x2. If x1 is less than x2, then y1 will be greater than y2, then the function is decreasing. All right, when I ask you to give increasing or decreasing intervals, I'm asking you for a range of x values. What are the x values over which the function's going uphill? What are the x values over which the function's going downhill? So just to make sure your eyeballs are reading graphs correctly, here's your vision test for today. Tell me in example 2, where, over what intervals is that function increasing? Where does it start increasing for the first time? Yep, right there is where it starts going uphill, and it goes uphill from 4 to 5, and again, those are x values. So I'd say it's increasing from 4 to 5. Is it increasing anywhere else? 6 to 7? I'm just going to use the union symbol to say that the function's increasing over this interval and that interval. And it's decreasing everywhere else, so how would you write the intervals over which it's decreasing? And I'm going to assume that they could only give me part of the graph there, but I'm going to assume that keeps going forever to the left and this keeps going forever to the right. Technically, I don't know that, but I know how they wrote the answers in the back of the book. So negative infinity up to where does it start decreasing? Stop decreasing. At positive 1, so negative infinity up to positive 1. What other portion is decreasing? It's decreasing from here to here. That's where x is 1 to 4. Is there any other decreasing portion? From here to here, 5 to 6. Would it be okay, since it's decreasing from negative infinity to 1 and then from 1 to 4, could I just say negative infinity to 4? No, because the function, it appears the function's not defined at 1. And so I don't want to say that it's decreasing at 1 if it's not even defined at 1. It looks like there's probably a vertical asymptote at 1. All right. What about this function, number 4? Where is it increasing? It throws some folks off first time they're getting increasing and decreasing. If I put arrows on math, they want to say it's decreasing everywhere because the arrows are pointing down everywhere, but just cover up the arrows and look at where the slope is going uphill from left to right, or where the slope of the tangent line would be positive. That is negative infinity up to negative 1. And then it's decreasing from negative 1 forever to the right, so negative 1 to infinity. One other thing, there's a little bit of disagreement in some textbooks whether or not to put brackets on the end of those intervals. I have seen books put brackets on negative infinity to negative 1 with a bracket, not the negative infinity, but the negative 1. In my opinion, and I think most books say that at negative 1, the function's not increasing or decreasing, it's just there. So they use a parenthesis on those intervals. But if you put a bracket, I wouldn't count it wrong. Some books do have brackets. Another reason it doesn't make sense to say to have a bracket is if you had a bracket on negative 1, you'd be saying that it's both increasing and decreasing at negative 1. In my opinion, that doesn't make sense. So I'm going to use parentheses on those intervals. All right, what about number 6? Give me the increasing intervals first. It's going uphill from negative 1 to 0. And where else is it going uphill? From 1. You didn't just say 1 to 2, did you? It looks like that's going forever to the right. So I'm going to say from 1 to infinity, it keeps going uphill. And then where is that function decreasing? Negative infinity to negative 1. And where else? 0 to positive 1. That's the decreasing intervals. All right, one more, number 8. Where is that function increasing? It's not increasing anywhere. It's not going uphill anywhere from left to right, so it doesn't have an increasing interval. You could either say it's decreasing from, now that graph looks like it stops. There's no arrow there, and it's not just running off the edge of the graph. So, well, actually, I know I'm given the domain there. The domain is 0 to 2 pi, so it does stop or start right here. And it's decreasing from that point, 0, to the end point of its domain, 0 to 2 pi. You could also say it's decreasing on, no, you wouldn't say all real numbers because you got a finite domain there. You've only got 0 to 2 pi, so you shouldn't say all real numbers. All right, so how does calculus tell us where a function's increasing and where it's decreasing? It's easy to look at the graph and see it, but how can you tell where it should be increasing and decreasing if you haven't graphed it yet? Got any ideas? How could we use calculus to tell us? Because the derivative is giving us the slope of the tangent line. Where the slope of the tangent line is positive, the graph's going uphill. Where the slope of the tangent line is negative, the graph is going downhill. Where the slope of the tangent line is 0, the graph is what? Constant, or a high point or a low point. All right, that's exactly what theorem 4.5 is. I think we should name it the Major theorem because Major thought of it. If a function, let f be a function that is continuous on a closed interval from a to b, and differentiable on the open interval a to b, if the derivative is positive for all x's in the open interval, then the function's increasing on that closed interval. Now, I don't know why they wrote increasing on a closed interval. We just talked about whether to use parentheses or brackets on that. I'm going to say books disagree, and I'm going to put parentheses on mine, and I'm not going to count it wrong on the test if you put brackets on yours. Where the derivative is negative, for all x's in the interval, the function's decreasing on the interval. And where the derivative equals 0 for all the x's in the interval, then the function's constant on the interval. Some guidelines for finding where the function is increasing or decreasing. If the function's continuous on the interval, to find the intervals over which the function's increasing or decreasing, locate the discontinuities and the critical numbers. Put those discontinuities and critical numbers on a number line. Let them divide your number line up into intervals, and then just use a test point in each interval to determine the sign of the derivative. Wherever the derivative is positive, it's increasing. Wherever the derivative is negative, the function's decreasing. Wherever the derivative is 0, the function's constant. So let's look at a few of those. Number 12 on page 223. Y equals x plus 9 over x. And all we're asked to do is find where the function is increasing and decreasing. I'm supposed to locate the discontinuities and the critical numbers. Does this function have any discontinuities? Yeah. Can't let x be 0. So I'm going to go ahead and make a note of that so I don't forget. Discontinuity at x equals 0. And how do I find critical numbers? What does that mean? Find the derivative, look for what makes it 0 or undefined. So the derivative would be, let's write this as x plus 9, x to the negative 1, just so I don't have to use the quotient rule. And the derivative would be 1 minus 9 over x squared. Now, is 0 a critical number because it makes the derivative undefined? Why? Because we've already identified what happens at 0. It's not a critical number if the original function's not defined there. It's an important number, but it doesn't meet the definition of a critical number. So I'm looking for what makes that equal 0. I could either get a common denominator, write it as a single fraction so that I could easily see what makes it equal 0, or I could just set it equal to 0 and solve it like that. Either way, I can see the critical numbers are what? Negative 3 and 3. So I'm going to put those critical numbers and the discontinuity on a number line, and I'm going to look at the sign of the derivative in each of those intervals. Any, meeny, miny, mo, what's your favorite number to the left of negative 3? Oh, you're so boring. Me too. If I let x be negative 4, would the derivative be positive or negative? Yeah, and I really don't care what it is. I just want to know if it's positive or negative. So if I let x be negative 4, that would be a positive over a positive, and a positive over a positive is positive. What's your favorite number between negative 3 and 0? I was hoping you'd say negative e, because that would have been so cool. But if it's negative 2, would this be positive or negative? Negative. And if it's positive 1, would this be positive or negative? Negative. And if we let x be 4, would this be positive or negative? Positive. All that's left is interpreting that number line. We could say the function is decreasing where? It's tempting to say -3 to 3, but why can I technically not say -3 to 3? Because the function is undefined at 0. There's a vertical asymptote at 0. So I don't want to say that it's decreasing where there's a vertical asymptote. I need to write that as -3 to 0 and then 0 to 3. For the very same reason that in this number 2, I didn't want to say it's decreasing from -infinity up to 4 if it's not even defined at 1. And the increasing intervals would be what? -infinity up to -3, and then 3 to infinity. Good. If this were business calculus, all that we would have, that's not totally true. Most of what we have in business calculus is polynomial functions, and polynomial functions are easy to work with. But engineering calculus, we're going to have some aliens and some e's and some sines and some arctangents. So we just need to do the same thing with those problems. Number 14. Aliens? I don't. What was the rest of the sentence? Oh, aliens. Aliens, natural logs. We do have aliens in engineering calculus. We have a restricted domain here. We're only looking at the graph of cosine of x over 2 on the interval from 0 to 2 pi. So whatever we list as critical numbers, make sure you're only listing the critical numbers from 0 to 2 pi, and it looks like 0 and 2 pi themselves are not included there. So is there anything that makes that undefined? That would be tangent. But no, there's nothing that makes cosine undefined. Cosine's defined from -infinity to infinity. So I don't have to worry about that. What about critical numbers? Before I do that, I need to write the derivative. What's the derivative of cosine? Think of that as 1/2 x. Don't use the quotient rule there. That's cosine 1/2 x. So what's the derivative of cosine 1/2 x? Negative sine of same old ugly times the derivative of the ugly, which would be 1/2. So -1/2 sine of x over 2. And now I'm looking for the critical numbers. The critical numbers are what makes that derivative either undefined or 0. Is there anything that makes sine undefined? Nope. So we're looking for what makes it 0. How do I find that? Right off the bat, I should divide both sides by -1/2 and not even have to worry about that. I'm just looking for what makes sine of x over 2 0. Hey, can I multiply both sides by 2 to clear out the fractions? Oh, I was going to love it if I could do that, but no. That 2 is part of the argument of sine. I can't clear it out just by multiplying both sides by 2. So how do I solve that? Just sit here until God whispers to me. That's the plan. Where is sine 0?
0, pi, 2 pi.
At all the whole pi's. So that's not what x is. That's what x over 2 is. X over 2 is any whole pi. Remember how we write any whole pi? Pi times any integer. That integer stands for any integer, and so that's any whole pi. Now we can multiply both sides by 2 and say x is 2 pi n. Are there any values of n that give us answers between 0 and 2 pi, not including 0 and 2 pi? Smallest thing n could be is 0, and then x would be 0, but this says don't include 0. And if n is 1, this is 2 pi, but this says don't include 2 pi. So there would be critical numbers for cosine 1/2 x, but they're not going to be on the interval from 0 to 2 pi. So I'm just going to say no critical numbers on that interval that we're given. To get pi, n would have to be 1/2, and we said n stands for any integer. If I let x be pi, then I'd have sine of pi over 2, and that's not 0, that's 1. Pi over 2 is right here. All right, what does that say about the function if there's no critical numbers? And I forgot to tell you a word I meant to tell you a minute ago. It's either always increasing or always decreasing. The name for that is strictly monotonic. Strictly monotonic means always increasing or always decreasing. So I'm just going to put that down in your notes just so you'll have it. No critical numbers means strictly monotonic. And that means always increasing or always decreasing. Other than graph it on my calculator, how can I tell whether it's always increasing or always decreasing?
Slope of the derivative.
Awesome. The sine of f prime of x on the interval from 0 to 2 pi. What's your favorite number between 0 and 2 pi? Pi. If I let x be pi, let me just say any, mini, miny, mo, negative infinity to infinity. If I let x be pi, then what's sine of pi over 2? 1. And 1 times negative 1/2 is negative. Negative doesn't matter what. So it's strictly decreasing. Or you could say decreasing on the interval from 0 to 2 pi. Now, one thing that will help you on test 3, if you can remember to do it, this is all about graphing, and you have a graphing calculator. I'm not going to take it away from you. You can check your work. You still have to show the calculus that supports what you write down, but if you want to make sure that that's right, make sure your calculator's in radian mode. And say f of x equals cosine of x over 2. If I only want to graph it from 0 to 2 pi, I can set my window accordingly. I can say x is 0, x max is 2 pi, and count by, what do you want to count by? Any, mini, miny, mo? I'm going to, darn it. Yeah, e is about 2.7. 2 pi is about 6.28. I could count by e's if I went all the way to 3e, I'm going to do it. I'm going to count by e's just because somebody said so. Oops. What about my Y max and min? Got any ideas what we should use there? What's the lowest value sign's going to attain? -1, and the highest value? 1. So let's be a little bit traditional on that. Just count by 0.1s are fine. This graph is going to be. My calculator's not freaked out by me counting by e's. It goes from +1 to -1. It's decreasing over that entire interval. So that supports the calculus. You gotta have the calculus. You can't just take a screenshot of your calculator and turn it in for the test. But you can check your answers, and you would be smart to check your answers. All right, let me see if anything weird happened on 16. If nothing weird happened, I want to skip it. I'll give you a shortcut version of 16. I want you to see it, but I don't want to spend a lot of time on it. Okay. Sine square x plus sine x on the interval from 0 to 2 pi again. 1 revolution of the unit circle, not including endpoints. Is there anything that makes that function undefined? Are there any discontinuities? Sine doesn't have any discontinuities. So we're ready for critical points. And where do we find critical points? Find what makes the derivative either 0 or undefined. How should I write that function before I start any calculus? I would be less likely to make a mistake if I wrote that as sine x squared. Which just happens to remind me that on the retest, some folks treated these two guys as if they meant the same thing, and they don't. This is the tangent being squared. This is the x being squared. I had folks on the test who just combined them and said it's 2 of these, and that wasn't right. All right, so back here. What's the derivative of sine x in parentheses squared? Derivative of ugly squared is 2, same old ugly, times what? Derivative of the ugly, cosine x. And the derivative of sine x, cosine x. Is there anything that makes that undefined? Nope. The only reason I wanted to do 16, it's not the calculus that's difficult. I want to give you some practice at solving trigonometric equations. So if I set that equal to 0, how would you go about solving that trigonometric equation? You look to see what you can factor out. That's very helpful that you can factor out a cosine x. And then you can set each factor equal to 0. I'm going to say if I set that equal to 0, I would subtract 1 from both sides and then divide by 2. So I'm looking for what makes cosine 0 or what makes sine -1/2. What makes cosine 0? Or where is cosine 0 on the interval from 0 to 2 pi? The half pies. Pi over 2, and this could be written as -pi over 2, but if I write it that way, it's not between 0 and 2 pi, so how should I write it instead? 3/2 pi. All right, so 1/2 pi and 3/2 pi. And then in what 2 quadrants is sine negative? 3 and 4. So here's the picture I have going on in my head. third and fourth quadrant where sine is -1/2, is that close to the x-axis or is that close to the y-axis if sine is -1/2? Close to the x-axis. X-axis is where y is either 1 or -1, and I'm not sure what I just said. X is either -1 or +1. Y is 1/2 at those angles close to the x-axis. So what's the name of this angle? This is 6/6 right here. That's 7/6. And that's 11/6. So those are my other two critical numbers, 7/6 pi and 11/6 pi. And here's the part that I don't want to spend a lot of time doing, just my test points. So I'm going to put them on a number line. What order do those go in on a number line?
Pi over 2, 7 pi over 6, 3 pi over 10, and 7 pi over 6.
And God probably just spoke to William and told him, because I decided that's what God does with William. But the rest of us might need to find a common denominator. It's helpful to me to have a common denominator. This is 3/6. This is 9/6. Now I can put them in order. 3/6 is pi over 2. Here's 7/6. And 3/2 is 9/6. And then 11/6. And so I'm just going to tell you that I did this yesterday and got that, and that, because I don't want to spend time plugging 5 test points into that derivative. It took a little while. You just tell me the increasing intervals. -infinity to pi over 2. 7/6 pi to 3/2 pi, and 11/6 pi to infinity. And then it's decreasing everywhere else. Decreasing from pi over 2 to 7/6 pi, and from 3/2 pi to 11/6 pi. Before you tell me what I did wrong, see if I can find it. -infinity to pi over 2, 7/6 pi to 3/2 pi, 11/6 pi to infinity. Decreasing from pi over 2 to 7/6 pi, decreasing from 3/2 pi to 11/6 pi. What?
Because it's only going from 0 to 2 pi, you would have negative and positive.
You're absolutely right. You're absolutely right. I should not have said from -infinity or to +infinity, because I'm talking about a closed interval here. I should say from 0 to pi over 2. You know what helps me remember that on the graph, and I didn't do it? If you give me a closed interval, I always draw a big line to say the graph stops here. And I forgot to do that on this graph. All right. If I was going to check this on my calculator, I would not count by e's, because it's pretty hard to tell where 11/6 lies in relation to e's. I could do it. I don't want to do it. So I would graph that function from 0 to 2 pi, counting by, what would you count by? Count by pi over 6, and then your tick marks are 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, all the way up to 12/6. So that's how I would check it. All right, let's see what the next thing on the notes is, oh, they're strictly monotonic. I forgot, but I typed that for you. Theorem 4.6 is the first derivative test, and I'm going to tell you what it says, and then I'm going to tell you why I never use it. The first derivative test says, let C be a critical number of the function. That means the function's defined at C, but the derivative is either zero or undefined. Let C be a critical number of a function f that's continuous on an open interval I containing C. If f is what? Differentiable on the interval except for possibly at C, then f of C can be classified as follows. If the derivative changes from negative to positive at C, then the function has a relative max at C. If the function changes from positive to negative at C, then the function has, I said the wrong thing, didn't I?
Yep.
Okay. If the function changes from negative to positive, then the function has a relative minimum at C. If the derivative changes from positive to negative, then the function has a relative max at C. If f prime of x is positive on both sides or negative on both sides of C, then f of C is neither a relative max or min. Does that sound like something you want to memorize? No, I don't have the brain space for that. It makes sense to me if my function is going uphill and then suddenly starts going downhill. What happened at the top? There's a max. Or if the function's going downhill and suddenly turns and starts going uphill, then obviously what happened down here? Okay, so I know what the first derivative test says, but it's not something I memorize. It's really not even something I use because I already have in the guidelines for finding critical points, I already have this number line with all these positives and negatives on it. I can tell you what happened at pi over 2. What is it? The function went from increasing to decreasing. There's a max at pi over 2. And at pi over 6, what? The function went from decreasing to increasing, so there's a relative min. So I really don't use the first derivative test if I already have that number line and the sign of the derivative all over it. What I do is say, going from uphill to downhill, going from downhill to uphill, going from uphill to downhill, going from downhill to uphill. And that tells me everything I need to know about relative max and min. All right, so examples here. Number 24. Let's see what the directions say. A part is find the critical numbers, if any. B is find the open intervals on which the function is increasing or decreasing. And C is apply the first derivative test to identify all relative extrema. I'm just going to say find the relative extrema. You don't need the first derivative test for that. You already have a number line in the B part. And then the D part, using a graphing utility to confirm your results. Please remember to do that on the test. If you make a mistake, or let's say you just have a different answer than the calculator, does that necessarily mean you're wrong? You could have a typo on the calculator. So it could be you that's wrong, could be the calculator that's wrong, which is really still you because you're the one who typed what went into the calculator, but at least tells you just to go back and look for a mistake, either on your calculator or in the calculus. All right, so 24. The A part says find the critical numbers. Means we need to find the derivative. Hey, does this original function have any discontinuities? No, domain negative infinity to infinity. Is there anything that makes the derivative undefined? Nope. What makes it 0?
Just 2/3.
2/3. Yeah, negative 2/3, because you'd add 4 to both sides and then divide by -6. So the only critical number is x equals -2/3. The B part says find the increasing and decreasing intervals. How do we do that? Set up a number line, look at the sign of the derivative to the left and to the right of -2/3. So what's your favorite number to the left of -2/3?
-1.
-1. -6 times -1 is +6. 6 minus 4, I don't even care what it is positive. Favorite number to the right of -2/3? 0. If x is 0, the derivative is negative. So where is the function increasing? -infinity to -2/3. And where is it decreasing? -2/3 to infinity. And the C part said find the relative extrema. It actually said use the first derivative test, but I already have that number line. And I'm thinking that function was going uphill, and at -2/3 it starts going downhill. So what does that mean there is right here at -2/3? There's a relative max.
Isn't it absolute max?
Hang on one second. Before I say 100% yes, I'm thinking. I'm at 99% yes right now. Now I'm at 100% yes. Because this is a quadratic function, means it's a parabola. A parabola only has one relative extrema, and it's at the vertex. You may have more maxes on some other polynomial functions, but here the relative max just happens to also be a absolute max. The directions are asking us for relative extrema, so that's why I wrote it that way. But in this case, it's an absolute extrema also. And the other day when I asked you what's the max value of a function on an interval, I told you just to give me the y value, because the y value is the max. The x value is where it occurs. But now we're trying to get points that by the time we get to 4.6, we're going to be graphing these points. So I want to go ahead here and give the whole point that I'll need to graph later on. X is -2/3, and I've already plugged that. Hey, where do I get the y? Do I plug that -2/3 into the derivative or the original function? If I'm graphing the original function, I plug it into the original function. I already know what the derivative is when x equals -2/3. What is it? 0. That's how I found the -2/3. So make sure you're putting the -2/3 back into the original function, and turns out that y is -2/3 as well. And then check it on your calculator. All right, I have 2 more and 10 minutes, let's say. I don't think there's anything particularly exciting about number 30. I'm going to skip it and just go to 32. Does that function have any discontinuities? Anything that makes it undefined? Tell me why you're sure of that, Sam.
Because a2 thirds is going to be the cube root of x squared, so the cube root of x can be anything.
I can take the cube root of anything. If this was, say, 3/4, then there would be a problem I'd have to watch out for. I couldn't take the fourth root of negative numbers, but I could take the cube root of anything. So no, there's nothing that makes that function undefined. The A part is find the critical numbers, and to find the critical numbers, I need the derivative. What's the derivative of x to the 2/3 minus 4? 2/3 x to the negative 1/3 plus 0. So I could write it as 2/3 cube root of x. Is there anything that makes that 0? The only thing that makes a fraction equal 0 is what? 0 in the numerator. If you can't get 0 in the numerator, there's nothing that makes that 0. What makes a fraction undefined? 0 in the denominator. Is there anything that makes that function or derivative undefined? 0. So 0 is a critical number. The function's defined at 0, but the derivative is not defined at 0. The critical number is x equals 0. The B part, look at the sign of the derivative. To the left and to the right of 0, and then tell me whether the functions, or where the intervals over which the function's increasing and the intervals over which the function's decreasing. Your favorite number to the left of 0? 8? 8?
What? So are you plugging it into our negative 8?
Oh, yeah. Eight's not to the left of 0. Not in my checkbook. Negative 8. Also seen that in my checkbook. If I let x be negative 8, I don't care about what the answer is. I only want to know if it's positive or negative. If x is negative 8, then what's the sign of the derivative? Cube root of a negative is a negative. 2/3 times a negative is a negative. So to the left of the 0, the derivative is negative. Don't automatically assume that to the right of the 0, it's going to be positive. It may not change signs there, but then again, it may. Does it? If we plug in a positive x, do we get a positive or a negative? Positive. And so what are the increasing intervals for that function? 0 to infinity. And what are the decreasing intervals for that function? Negative infinity to 0. And then the C part says, identify any relative extrema. I could use the first derivative test, but I'm going to look at what I already have and say, if that function went from going downhill at 0 to going uphill at 0, then what does that mean happen right at 0? There's a relative min. Relative min when x is 0, and where do I plug that 0 to get the y? The original function, because I'm graphing the original function. If I let x be 0, y is negative 4, and then I can check that on a calculator. All right, we actually have 2 days to cover 4.3, not because it's difficult, but because most of what we did today were algebraic functions. Guess what that means I saved for tomorrow? Transcendental. Transcendental. Tonight's homework, 3 through 31 odd.